This is a video about electrophilic aromatic substitution. It's going to involve an aromatic system, typically benzene or some derivative of benzene. So let's start out with the benzene ring. Very useful in these reactions in terms of keeping track of things to have any hydrogens that are on the benzene ring included in the structure. So please fill in the hydrogens on your structure now. Here are the hydrogens, 6 of them in benzene. So that's the aromatic part of electrophilic aromatic substitution. And then we need an electrophile. Let's keep it general to begin with. So here's some generic electrophile, E+. And then along with that generic electrophile, there will be some negatively charged counterion, which I'll just call X-. So the first problem I would like you to try to think about is push an arrow between benzene and E+ and write down the result of that arrow pushing. So just one arrow, that's all I'm asking for at this point. Well, we need a source of electrons. This is not a source of electrons. That's where the electrons are going to be flowing to because it's the electrophile. So the source of electrons will be the pi system of benzene. We know that benzene is aromatic, so the electrons in that pi system are relatively stabilized. They're all in bonding molecular orbitals. Nevertheless, if there's enough activation energy present, we might imagine something like this. So here's the arrow that perhaps you wrote. If you didn't get that far, use this arrow to draw the next structure. So what would the intermediate in such a process be? And hopefully this is reminiscent of the chemistry of addition of electrophiles to carbon-carbon double bonds to alkenes that we covered last semester. So write the product or the intermediate. The intermediate structure will have given up one of the 3 double bonds of benzene. So there will still be 2 double bonds in those positions. Let's be sure we include the hydrogens because all of the 6 hydrogens from the original structure are still there. And then to one end of this double bond, I'm going to be attaching the electrophile. Because the 2 ends of this double bond are the same, it's up to you, the choice you make, but later on that will matter. So let's just put the electrophile on this particular carbon. There is a hydrogen on that same carbon, let's not forget that. And we also have to conserve charge, so if we combined a neutral benzene and a positively charged electrophile, there must be a positive charge somewhere here. So where is it? There it is. And then to go along with this, we have X-. Look at this intermediate. The next part of this exercise is thinking about the properties of this intermediate. This is really, it's a carbocation. Just maybe pause the video on the view of this carbocation and think a little bit about what your feelings are about that carbocation. Is it a good carbocation as far as carbocations go? And also, remember carbocation fates from last semester, the things that carbocations can go on to do. So think about maybe a couple things that in principle this carbocation might go on to do at this point. The first thing we might notice about this carbocation is that it is allylic. In other words, it has a double bond next door, so that there are some other resonance structures that one could write. So please pause the video and write down a couple other resonance structures of this carbocation. In terms of resonance structures, we could imagine the typical allyl cation type of electron pushing. So that would generate a structure of this type. We're keeping all the hydrogens in our picture because otherwise it actually is quite easy to get mixed up in terms of where the hydrogens are, where the charges are, and so on. So that migrates the positive charge in the second resonance structure from this carbon to this one. Notice, as is typical for allyl systems, we skip over the carbon that's in between. And now if you look at this, this is allylic again. So there's another resonance structure. Keep the hydrogens in there. Like that. So in terms of resonance delocalization of the positive charge, this looks pretty good as far as carbocations are concerned. But don't forget that we had to give up the aromatic ring over here from the starting material in forming this intermediate carbocation. Okay? So we will call this carbocation, it's a cyclohexa six-membered ring. It has two double bonds in it. So it's a cyclohexadienyl cation. So this is the key intermediate in electrophilic aromatic substitution. So the next part of the problem, remember, was what could this carbocation potentially now do? Well, one of the things we said carbocations could do would be to add a nucleophile to the positively charged carbon. So if we were to do that, what's the nucleophile? Well, maybe X minus. And so we could add X minus to the carbocation. So that might be option one. So this would be addition to the carbocation. And so the next question is, if this were to happen, this would be the final product right here. Would this final product be aromatic? So think about the criteria for aromaticity that we talked about last week and decide whether this addition product, where we've added E and X to the original double bond of the benzene ring, whether that would be an aromatic product. Remember, one of the criteria for aromaticity was that there has to be a ring, and there is a ring. But the other one was that we had to have a contiguous array of 2p orbitals all the way around that ring. And the problem here is that while we have an sp2, 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 4 sp2 hybridized carbons in the ring, the other two carbons are sp3 hybridized. So there's no 2p component at either of those sp3 hybridized carbons. So this is not aromatic. So that is perhaps not the most favorable product because in the end we've given up the aromatic ring. So think about what would be a different carbocation fate besides addition of a nucleophile to the carbocation. What's another thing that carbocations can do? Well, maybe you came up with elimination. That is to say, we remove a hydrogen from the carbon next door to the carbocation to make a double bond. So let's go back to this structure right here. And if we look next door to the positive charge, if we were to remove this hydrogen right here using some base, and we do have X minus around, so please think about how X minus, by removal of this proton, could carry out an elimination reaction, and the product will restore the benzene ring. So see if you can push those arrows. The second part of an E1 type elimination is the base removes a proton. You use the electrons from this CH bond to come there and make a double bond. And so if we come over to this side, and then the other product would be HX. So let's go back to the name, electrophilic aromatic substitution. We said the aromatic part comes from the fact that you have an aromatic ring. Notice the aromatic ring is present both at the beginning of the reaction and at the end of the reaction. The electrophilic part comes from the fact that there's some electrophile that reacts with the aromatic ring. And finally, the substitution part comes from the fact that you are replacing or substituting a group on the benzene ring, in this case a hydrogen, and you're substituting that hydrogen with E, and then the pieces that are left over at the end are the counterion from the original electrophile, and this hydrogen right here, which is lost as a proton. So the byproduct then would be HX. So that's the overall transformation. Mechanistically, the key is this initial step in which the benzene ring, the pi electrons of the benzene ring, attack the electrophile and make this cyclohexadienyl cation. So